Now, we talked quite a bit about spans when we talked about column vectors. If you go back and see here, we talk about, remember this chapter on spanning sets, span of a set of vectors. So we talked quite a bit about spans, and we actually expressed null spaces and column spaces as spans of sets of vectors. So we're going to do something similar. As I've mentioned in this chapter on vector spaces, we're generalizing things that we've seen before. So we're going to do the same thing here. Okay, so let's repeat the definition that we used before, but in a more general context. So suppose that V is a vector space given n vectors, u1 through un, and n scalars, alpha 1 through alpha n. We define the linear combination as each scalar multiplied by corresponding vector added together. No, there's no difference between this and our earlier definition. Just you need to reconceptualize that these vectors can be anything, not just column vectors. For instance, you can have a linear combination of matrices. Here in this example, 4 times this matrix X minus 2 times this matrix Y plus 3 times this matrix Z. And you add very similarly. Actually, you can see that these are pretty much like vectors, only they're just rearranged. Instead of in a column, they're arranged in a table. Okay, but as I said, we can do linear combinations of any type of vector, even polynomials or functions or any other type of vector. All right, now let's define the span. The span is basically the set of all possible linear combinations achieved from a certain set of vectors. So the formal definition, given a set of vectors S consisting of n vectors, t vectors, u1 up to ut, their span is the set of all possible linear combinations of the t vectors. Symbolically, we can write it this way, that the span of S, use these angle brackets for span, is equal to the set of possible linear combinations. This is how you write an arbitrary linear combination for all possible constants and for all indices between 1 and t. Okay, so let's tie this together with what we've been talking about in subspaces, that actually it's true that the span of any set is a subspace. Now, it might be the whole space, or it might be the trivial space, but it will always be a subspace. Okay, so let's look at the formal statement of this theorem. Suppose V is a vector space, given a set of vectors, a set of t vectors as before, then their span is a subspace. Now, there's 3 things we really need to show. We need to show that the span is non-empty. We need to show that the span is closed under addition, and that the span is closed under scalar multiplication. Okay, so let's go to those 3 conditions. Those are the 3 conditions of Theorem Tss. You can see that back here. If we just go back quickly, you can see that you need to show these 3 conditions. Non-empty, closed under addition, closed under scalar multiplication. Okay, so first of all, we can show that this is non-empty. There are various ways you can do this. Here in this way, he shows that we can write the 0 vector as a linear combination of these vectors where all the constants are 0. Okay, so the 0 vector is a vector. It's not an empty set. So we have a set that's non-empty. We have the span is non-empty. All right, so we're done with non-emptiness of the span. Let's now show that the span is closed under addition. That's this condition here. The span is closed under addition. So we're assuming x is in the span and y is in the span. Now, if x is in the span, we can write it as a linear combination of the t vectors u1 through ut. If y is in the span, we can similarly write it as a linear combination. Now, this proof should seem very familiar. We've done exactly this kind of manipulation before. Let's take the sum of these 2 vectors, x plus y. Now, we can do all kinds of commutativity, associativity that we've done before. Notice that here's a term that involves u1 in x, here's a term that involves u1 in y. We want to group these 2 together. We want to group these 2 together. We want to group these 2 together. And that's exactly what's done here. He groups the two terms with u1 together. He groups the two terms with u2 together. All right. Now, what do we have here? We have a constant, a scalar, times u1, plus a scalar times u2, plus blah, 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 up to scalar times ut. This, in fact, is a linear combination of the vectors u1 through ut. But that means that this vector is also in the span of S. That's by the definition of span. That's what it says here. Since each alpha I plus beta I is a scalar, here we have a linear combination. This means that x plus y is a linear combination, and therefore it's in the span. All right, so now we've shown closed under addition. All right, last one, we need to show that the span is closed under scalar multiplication. What does that mean? If I take any vector in the span and multiply it by any scalar, then that product must also be in the span. Okay, so let's check it out. Now, if x is in the span, we can write it in this way, just like we did in the previous step. Now we need to show if we multiply this by alpha, we'll still get something that's in the span of u1 up to ut. So if we multiply by alpha, we can distribute in, and we can do the associative property of scalar multiplication. Now what do we have here? Here we have a new scalar, new scalar, new scalar, new scalar. Here we have scalar times u1, scalar times u2, all the way up to scalar times ut. That means that we have a linear combination of the vectors u1 up to ut. So we've shown that alpha x is a linear combination, therefore alpha x is in the span. Okay, so that tells us that the span of any set of vectors is a subspace. Okay. All right, so let's do an example. Let's take, we showed a subspace W of the set of all polynomials of degree 4. All right, so let's construct a span within W. Here, let's consider these two polynomials. Here's one and here's one. Okay, now these are both polynomials. They both have degree 4 because the leading term is x to the 4th here. Now you can check, I'm not going to check, but you can check by plugging x equals 2 into these equations that 2 is a root of both of these. So both of these are in W. Okay. All right, now the span of these two sets, which we call U, is a subspace. And since it's in W, it's a subspace of W. So as he says here, we have a vector space V, we have W inside of V, and we have U inside of W. Now at this point, it's possible that U is in fact equal to W. We haven't checked that, but we do know that at least it's a subspace of W. All right, now the span of these two polynomials is a subspace. We can easily form linear combinations. Here he took 3 times the first plus 5 times the second. Here he took minus 2 times the first plus 8 times the second. And these are also in the span. These are also in U. Okay. All right, now another question is, can you tell whether or not, how can you tell when a vector is in the span of two vectors? We've had this kind of problem before as well. Okay, so let's check this polynomial here. Is it possible that this polynomial here is in the span of the two polynomials that span U? So is this polynomial in the span of U? Okay, well, if it is in the span, then we can write it as a linear combination. Okay, so that means that this polynomial here should be expressible as alpha 1 times the first polynomial plus alpha 2 times the second polynomial. Now if we rearrange, we get a polynomial and we have coefficients that are expressed in terms of the unknown constants alpha 1 and alpha 2. Now in order for this polynomial here, 3x to the 4th minus 7x cubed, etc., to be in the span, we must be able to solve these equations. Alpha 1 plus 2 alpha 2 equals 3, minus 4 alpha 1 minus 3 alpha 2 is equal to minus 7, and so on and so on. Okay, so we have these equations here, and we know perfectly how to do this. We have an inhomogeneous system of equations. We do the augmented matrix, we reduce, and lo and behold, there's a pivot column in the last column. Okay, and since this is an augmented matrix, if you have a pivot in the last column of an augmented matrix, that means that there's no solution. No solution. Okay? All right. So let's consider another example. Suppose we have the 3 by 2 matrices, and let's consider the span of a set of 3 by 2 matrices. So here we have 5 3 by 2 matrices, and we want to consider the span. We know that the span is a subspace. So the question is, we can ask the same question. Of any 3 by 2 matrix, is that matrix in the subspace? So let's consider this particular matrix, and the question is y in the span of S? So that's the question. How do we determine that? All right, well, we can use the same sort of strategy. If y is in the span, then y can be expressed as a linear combination. We can write an arbitrary linear combination. And once we write an arbitrary linear combination, we will obtain equations for the constants. So let's see how that plays out. Okay. All right, so here's our matrix. We want to tell if that's in the span. So here's our arbitrary linear combination of the 5 vectors in S, that span S. And we can write equations for each component of the vector. For instance, the first component of this linear combination is going to be 3 times alpha 1 plus 1 times alpha 2 plus 3 times alpha 3 plus 4 times alpha 4 plus 3 times alpha 5. Okay, so that's the first component of the linear combination. So this matrix expresses all of the components of the linear combination of these 5 vectors. All right? Now, in order for this matrix here, to be a linear combination, we must be able to express all of the entries of this matrix as linear combinations here. So we must be able to express 9 using this expression, 7 using this expression, and so on. So here we have expressions here. We have expressions for the 5 constants that are used in the linear combination. And here we have familiar territory. We have a set of linear equations for unknowns. We can set up the augmented matrix. We can reduce it. Turns out in this case that the pivot column is not, the augmented column is not a pivot column, so there is a solution. So that does mean that y is in the span of S. We can solve for these constants. That means that we can show that we can express y as a linear combination. Okay, we can do the same thing with this one. Okay, now this is quite repetitive. You really have the same expression for the linear combination. The only thing that's changed is the constants on the right-hand side. So we can set this up again, and it turns out in this case that the augmented column is a pivot column. There's no solution. Okay, and we'll stop there. Okay, so this subsection really contains some corollaries from the previous section. Corollary means a very automatic consequence, and we can pretty much just get by mentioning these things. The column space of a matrix is a subspace because it's the span of the columns. Okay. The row space of a matrix is a subspace because it's the span of the rows. The left null space of a matrix is a subspace because it's also a null space. And we already showed that a null space is a subspace. So that pretty much takes care of that subsection.